Good morning, everybody. Welcome back to Math 105. I hear you. Plan for today is we're going to finish our discussion of Standard 7, talk a little bit more about logical syllogisms, and then we are going to jump into Standard 8 and look at Lewis Carroll puzzles. Got my usual office hours today and Wednesday at 10 o'clock and from 2 to 3. Tomorrow, I have my mostly normal office hours from 10 to 11 and from 1:30 to 2:30. My office hour tomorrow morning, I have to cut a half hour short because of a department meeting. And as far as upcoming homework assignments go, I posted the Standard 7 quiz already on Blackboard. It will be due on Wednesday night. And don't forget, you also have a quiz from Standard 6 still that will be due tonight. Kind of the plan is, we spend the first half of class looking at a few more examples from Standard 7, just because thought it'd be good to get a little bit of extra practice in with that. And then we'll start Standard 8 today and finish Standard 8 up on Wednesday. Any questions or comments before we get started for today? Yes?
Are we going to be going online, or have you not decided yet?
Yeah. Good question. Right now, the plan is to stay in person, but that is very likely to change based on what's going on at the college. We are going to be in person until further notice, but don't be surprised if we end up going online.
Okay, thank you.
Good question. If we stay in person, we'll certainly be going full all masks for quite a while longer. Any questions or comments? Okay, so you may recall. Before I forget. What do you call a mathematician who enjoys working with farm equipment? A mathematician who enjoys working with farm equipment, you call a protractor. Okay, so you may recall, get that piece here. You may recall from last time we said that a logical syllogism is just going to be a set of 3 statements that make some sort of logical argument that has to hold true if it's logically valid. The first 2 statements we called the hypothesis of the syllogism. The last statement we called the conclusion. And we had 4 logical laws that we had talked about that can be used to determine when a syllogism has to be true or when does a syllogism not necessarily have to logically hold. And the 4 laws that we kind of established back in Standard 6 were the laws of Modus Ponens, which said that if P implies Q and if P is true, then Q has to be true. We have the law of Modus Tollens, which said that if P implies Q and Q is false, then P has to be false. We had the law of transitivity, which says that if P implies Q and Q implies R, then P has to imply R. And finally, we have the law of Destructive Syllogism, which says that if P or Q has to be true, and P is not true, then Q has to be true. And those are kind of the 4 laws that we established back in Standard 6. And we've already looked at a couple examples of how you can take a logical syllogism, transform it into a symbolic form, and they kind of use the symbolic form to determine whether or not it makes a logically valid argument by seeing if the symbolic form translates to something that's a tautology or not. But I thought what we would do today is to just go through a couple more examples so everybody's on the same page. We all kind of have a good sense of how can you look at a syllogism, how can you rewrite it in kind of this nice way, and in symbolic form, and how can we determine if it's logically valid. So first one I'm going to look at is on the, let's see, what page of this packet is this? 1, 2, 3, 4th page of the packet, starting with all sailors have fishing hats. So here's how this syllogism goes. All sailors have fishing hats. Dr. Arn isn't a sailor. Therefore, Dr. Arn has no fishing hat. So, typical syllogism in that we have two initial statements that all sailors have fishing hats, and Dr. Arn isn't a sailor. Therefore, Dr. Arn has no fishing hat is going to be our conclusion. If we wanted to write this in symbolic form, I think we need to kind of have two base statements here. This is going to be one where we just have a P state-based statement and a Q-based statement that we have to work off of. Anyone like to have good candidates for what P and Q might be here?
Sailors and having fishing hats.
Sailors. Okay? Sailors is a noun, not a statement. How could we transform something about like sailoring into sailoring? What are we talking about, Dr. Gersel? How could we translate maybe this word into a single statement?
Being a sailor.
Yeah, maybe just something like P could be it is a sailor, or they are a sailor. Yeah, that would certainly be one kind of way we could start things off with a base statement. Okay, I'm on board with that plan. And let's see, someone from this half of the room. If our statement P is just going to be something along the lines of they are a sailor, which I think could apply to give us everything we need for, say, statement number 2, what else could we have as our other base statement that kind of fills in the second part of the first statement?
They have fishing hats.
They have fishing hats. I'm just going to say a fishing hat. I guess you could have more than one, but the exact number doesn't really matter here for the purposes of our argument. So, how could we rewrite, if statement P is they are a sailor, and statement Q is they have a fishing hat, how could we write the first statement, all sailors have fishing hat, in symbolic form?
If P then Q.
If P then Q. P implies Q. P implies Q. If they are a sailor, then they have a fishing hat. It's something that's logically equivalent to just saying all sailors have fishing hats. Is that a and or
No,
okay?
sorry.
Sometimes it's hard to tell. How about statement number 2? Dr. Arn isn't a sailor. What?
Negation P.
Negation P. The fact that we're talking about when we're talking about a specific person, they, we are talking in statement B, in the second statement about a specific person, Dr. Arn, but that doesn't really matter who we're talking about. We could replace Dr. Arn with Dr. Van Orman or Dr. Talor or Big Bird from Sesame Street. The exact person that it's talking about doesn't really affect the logic of the argument at all, as long as we're consistent about it. So P implies Q, not P. Therefore, not Q. Dr. Arn has no fishing hat. So P implies Q, not P, therefore not Q. How could we write that out as a single compound statement? Using sort of a compound form that might look like one of these laws or something that's at least similar to one of these laws.
If P implies Q and not P, then not Q, then not Q star.
Like that? I like it. Yeah. We could write this out as a single symbolic statement as saying, if P implies Q and not P, then not Q. And so that would be kind of our way of taking the syllogism and writing it out in symbolic form like this. So what do you all think? Is this going to come out to be a valid argument? Or, meaning, is this symbolic statement going to be a tautology, or is there a scenario under which this big symbolic statement could come out to false?
It's not a tautology because Dr. Arn could just like fishing and have a fishing hat but not actively sail. He could just fish from a riverbank.
Yeah, so just because he isn't a sailor doesn't mean he doesn't have a fishing hat. Lots of places to fish that don't necessarily involve being on a sailboat. And so the symbolic statement does not look like one of our laws. We don't have a law that says if P implies Q and not P, then not Q. It sort of looks similar to the law of Modus tollens, in that Modus tollens sort of has all the same pieces, but in Modus tollens we're saying if P implies Q and Q is false, and Q is false, I should say, then P has to be false. If P implies Q and P is false, then not Q, we could have that if P is a false statement and Q is a true statement, this implication would come out to false. If P is true and Q is false, this statement would be false. Because if P is true and Q is false, sorry, if P is false and Q is true, I mean. That. Because if P is false and Q is true, then P implies Q will come out to true. Negation of P would also come out to true, since P is false. So this would all come out to true, but not Q would come out to false, because Q is a true statement. And of course, if you wanted to, you could draw a truth table to help us see this. If just kind of looking at the different pieces is a difficult task. Anyone like to see the truth table for this one? Should we skip it? Yeah. If you wanted to, you could certainly draw out a truth table the way we've kind of been doing for the last couple of weeks. And in the P false, Q true row, this should come out to false. So it would be true in all other scenarios. So what can we conclude about our original syllogism from the fact that its symbolic form doesn't come out to a tautology?
It's a contingency.
It's going to be a contingency, this statement here, and what does that tell us about the syllogism itself?
It's not a valid syllogism.
Yeah, it's not logically valid. But you're right, that's because the symbolic form, that's because it comes out to something that is a contingency and not a tautology. So because it comes out to a contingency, this syllogism is not logically valid. Any questions about how we interpreted this one? Okay, so what I would like for you all to do is take a couple minutes and see if you can look at the next syllogism on this page. Tom gets gas whenever he goes to the gas station. Tom did not get gas, therefore Tom did not go to the gas station. I'm going to take just a couple minutes and see if you can determine whether or not the syllogism after this one in the packet is logically valid or not. And then once you've had a chance to think about it a little bit, we'll come back together as a class and talk about it. So normally I would say if you feel comfortable doing so, you can talk to your neighbors about this. And if you both feel comfortable doing so, you're certainly still welcome to. I'm going to stop saying that in class though, because COVID rising. So yeah, I'm going to stop saying that. That's not to say you're forbidden to do so, I just don't want to necessarily encourage it. Okay, so would anyone like to share what they thought about this one? Anyone have a way of sort of breaking up the individual pieces into base statements? In other words, come up with like a P and a Q like we did in the previous syllogism.
Statement P can be Tom goes to the gas station.
Tom goes to the gas station, okay?
And then statement Q can be Tom gets gas.
Just a second. Okay.
And going back up to the statements, you can rewrite this as P implies Q, and then negation of Q, and then negation of P. And so then when you write that all out, it's literally just
Well, hold on just a second. You're flying through this, and that's great.
Sorry.
I just want to make sure the rest of the class has a chance to catch up. So our proposed P is Tom goes to the gas station, and our Q is Tom gets gas. Tom, I hope you haven't been eating too many. This is funny because my dad's name is Tom, and he frequently has gas, but not of the same kind. So you propose that our first statement, Tom gets gas whenever he goes to the gas station, can be written in the form P implies Q?
yes.
What do you all think? It's written in a little bit of an unconventional way, but I think I agree with your interpretation. Tom gets gas whenever he goes to the gas station is really the same thing as saying if Tom goes to the gas station, then Tom gets gas, which would be kind of a more standard way of saying if P, then Q. But yeah, I'm on board. And then Tom did not get gas will just be not Q. Therefore, Tom did not go to the gas station, not P. So, anyone have a way? I'm gonna cut off your part of the argument because I want to get someone else in class involved. But good job. How can we write this out as a single compound symbolic statement? The argument P implies Q, not Q, therefore not P.
P implies Q and not Q, and then implication arrow, not P.
P implies Q and not Q implies not P? I like it. Saying if first statement and second statement hold, then that implies third statement. Is this a logically valid? Does this make for a logically valid argument?
It basically displays modus tollens.
It is exactly the form of modus tollens. Yeah, so we can then say, by modus tollens, this has to be a tautology, and therefore our syllogism is logically valid. Where's Ponens, not Ponens? Any questions about this? Did anyone have a different choice of a base statement for P and Q? Because when I looked at this, I actually said my P was Tom gets gas, and my Q was Tom goes to the gas station. And then when I wrote it out like that, my symbolic form ended up being Q implies P, not P, therefore not Q. If I did it that way, and then got a single symbolic statement of Q implies P and not P, together implies not Q, would that still be a tautology? And if so, what logical law would cause this to be a tautology? There's a string floating in front of my face, I just noticed. Okay, I'm sorry, that's distracting. Would this still make Q implies P and not P implies not Q? Would that still make for a logically valid argument? We swap the order of all our Q's and P's.
Yes, because the variables still stand for the same segments of modus tollens. It's just you switch the names of it. So it's saying the same thing, just with different variable positions.
Yeah, I agree. If we end up having to swap all of our Q's with P's and the modus tollens, we could just as easily have said modus tollens. We could have just as easily said modus tollens had the form if Q implies P and not P, then not Q. The fact that we chose P and we put the P before the Q in the original implication didn't matter. It's just that once we set what our Q is and what our P is, we need to have them all in the same order. So this would be just as valid a logical argument for modus tollens, even though the variables are kind of written in a slightly different order. And so if you want to call this one P and this one Q, or the second one P and the first one Q, or if you wanted to refer to the first one with an X and the second one with a smiley face, it doesn't really matter. As long as you have the same pattern of if first statement implies second statement and negation of second statement, then negation of first statement, no matter what variables you're actually referring to these statements by, that creates a tautology through the law of modus tollens. Just wanted to make sure you all could kind of see how I like to try and be consistent in kind of the examples I do with the terminology of P's and Q's. But if you write them in slightly different ways, that doesn't mean they're not logically valid. That just might mean you need to kind of reverse the order of some things in your head when you look at these different logical laws. Any other questions or comments? Okay, that's going to do it for Standard 7. I put a lot more examples in this packet, and I encourage you to try those on your own. I have some examples that also use law of transitivity, law of destructive syllogism. Now I'm going to talk about Lewis Carroll puzzles. And before I do that, so this is going to be Standard 8, I want to talk to you about a mathematician named Charles Dodgson. So a mathematician, lived many, many years ago. Famous for kind of doing work in geometry, linear algebra, mathematical logic. There's a packet. Yes, there is a new packet. He also is famous for his pen name, Lewis Carroll, and writing Alice's Adventures in Wonderland and Through the Looking Glass, and lots of other kind of fantastical stories. Well, he's kind of in modern days known more for his fantasy writing. His vocation was actually work as a mathematician. And as a mathematician, one of the things that Lewis Carroll did was to come up with kind of a sequence of puzzles that he developed in order to help people kind of improve their logical thinking skills. And so I thought it would just kind of be fun. Standard 8 is going to be one that's just more of a for fun standard, to sort of trying to interpret and look at different logical puzzles. But I also think but these puzzles I think are kind of very useful for what we're currently doing, and that they're all going to be puzzles that involve taking statements, writing them out symbolically, and then trying to come to logically valid conclusions, similar to what we were doing when we were looking at syllogisms in Standard 7. So let's look at an example of one of these puzzles. Oops, no, what's that? All babies are logical. Anyone who can manage a crocodile is not despised. It seems in the packet I misspelled the word despised. Illogical people are despised. Is this a logical syllogism? It's a set of three statements. All babies are illogical. Anyone who can manage a crocodile is not despised. Illogical people are despised. I claim this is not actually a syllogism, though, because it's not making any sort of logical argument. It's just saying three statements that are all kind of about similar things, but this is not making any sort of claim that the first two statements have to imply the second, or the third statement. We don't really have a hypothesis, therefore conclusion sort of structure to this. So our goal, whenever we're looking at a Lewis Carroll puzzle, our goal is always going to be this. We're going to find a way to string all three statements together to arrive at some conclusion. sort of like, in other words, it's sort of like we're being given the hypothesis to a logical argument, and we have to be able to produce what the logical argument is based on all of this information. So typically, what that means is I'd like to be able to say, make a single statement that's going to say if A, then B, and somehow that if A, then B, the argument for showing that that has to be true involves using all of the individual three statements. So in other words, we need to somehow be able to construct a new statement that relies on all three of these being true in order for our new statement to be true. And typically, the way we do that is going to be write out all of the statements symbolically. And then we'll actually see kind of how can we sort of draw connections between the different statements using their symbolic form. So all babies are logical. Let's start off by trying to write this one out symbolically. Well, I claim this is going to be we could rewrite all babies are logical in the form of an if-then statement. So how could we rewrite all babies are illogical as an if-then statement?
If it is a baby, then it is illogical.
If it is a baby, then it is illogical. Yeah, that's certainly a way we could write that out symbolically. So if we make, let's say, we're going to be using lots of statements. I'm going to typically use like the letters referring to something found within the statement instead of just P and Q. So if we let our B statement be, it is a baby, and our I statement is going to be, it is illogical, then our first statement can be written in the form B implies I. If it is a baby, then it is illogical. Now our second statement, anyone who can manage a crocodile is not despised. How can we write that as an if-then statement? If blank, then blank. Anyone who can manage a crocodile is not despised.
If they can manage a crocodile, then they're not despised.
If they can manage a crocodile, then they are not despised. Yeah, so let's say we can make an end statement for they can manage a crocodile. Crikey. Or D is going to be they are despised. If our M statement is they can manage a crocodile, and our D statement is they are despised, how could we write that? How could we write the second statement in our puzzle out symbolically?
If M, then not P.
If M, then not P.
Or D.
Like that?
She said D.
Oh, D. Yes. Sorry, I've done so many of these with P's that I feel like there needs to be a P subconsciously somewhere in here. So now we have our second statement written out symbolically. How about our third statement? Illogical people are despised. I think we could write this out symbolically now using the same. We don't need any more base statements. We can use ones that we already have. How could we combine a couple of these to give us something that's logically equivalent to saying illogical people are despised?
I implies D.
I implies D. Bingo. So now we've written out all the statements in our puzzle symbolically. B implies I, M implies not D, I implies D. And now we're going to write out the contrapositives of each of these. or if you may remember, that we said the contrapositive of a statement Q implies P is not Q implies not P. And we also proved way back in Standard 5 that a statement P implies Q and the contrapositive not Q implies not P are logically equivalent. And so if we take the contrapositives of each of these, the contrapositive of B implies I is going to be not I implies not B. The contrapositive of M implies not D is going to be what? Why don't we take the contrapositive of M implies negation of D?
D implies not M.
Yeah, we would technically get not D implies not M, but not D is the same as D. And the negation of I implies D is going to be not D implies not I. I need more board space. Don't really need our base statements anymore, so I'm going to give myself a little extra room. So now, here's going to be our goal. Find a way to start keeping in mind that B implies I is logically equivalent to not I implies not B. M implies not D is logically equivalent to D implies not M. And I implies D is logically equivalent to not D implies not I. What I would like to do now is to find a single string of implications that starts at one of these letters, B, I, M, or D, goes through all of the other letters, and so we somehow end up with a string of implications that starts with one of these letters and ends up at a fourth letter that somehow ends up using all three of these statements or the contrapositives. So let's see if we can do that. So basically, we need to be able to start at one of these letters and be able to go B implies I implies M implies D, or D implies I implies not M implies not B. Something along those lines. Does anybody have a letter that they would like to start at?
B.
Okay? You want to start at B? Okay. So now we have a starting point. Our starting point is going to be B. Do we have a statement that tells us something that B has to imply?
B has to imply I.
Yeah, we can use the first statement to tell us that B has to imply I. What do we have another statement that I implies, according to one of the three things we've written down symbolically?
D.
Yeah, we could use our third statement to say that I has to imply D. If I is true, then D is true. And finally, can we use one of our three symbolic statements to tell us something that D has to imply?
Not M.
Not M. And this, by the way, is why I had you write out all the contrapositives. Is because sometimes the original three symbolic forms, we can't just look at this. There is none of these that says D implies anything. But if we take the contrapositive of the second one, we get that D has to imply not M. So sometimes the original symbolic form doesn't get you to where you need. It's sometimes useful to be able to use the contrapositive of something rather than the original implication as was written. So B implies I implies D implies not M. So the first line tells us that all babies are illogical. The third line says that illogical people are despised. The second line tells us, if we rewrote it in contrapositive form, the second line tells us anyone who's despised cannot manage a crocodile. And so our overall implication where we kind of form a single implication that uses all three of these base statements, is going to be B implies not M, or all babies cannot manage crocodiles. So this would be sort of like we're coming up with a conclusion that has to follow from this hypothesis, where this technically isn't a syllogism because syllogisms have two-line hypotheses. This is a three-line hypothesis. But in essence, we're constructing the conclusion to a logical argument that has the hypothesis with these three lines in it. If all three of these statements in the hypothesis are true, this has to be our conclusion. Any questions or comments about what we've shown? Okay, same starting point, or same argument. Is there another set of four statements that we could have constructed that would allow us to come to a conclusion? We started at B and ended up at negation of M. Is there another place that we could have started?
We could have gone the other way instead and started with N and ended up with not B.
Okay, start with M and end at not B. Let's see. If we have M, our second statement tells us that the negation of D has to be true. Negation of D, according to the contrapositive of the third statement, not D has to imply not I. And by the contrapositive of the first statement, not I has to imply not B. And so we could have written this in a different form. M implies not B, which we could write as saying anyone who can manage crocodiles is not a baby. B implies not M, M implies not B. And this would have been another logical argument that we could have constructed that would have gotten us to the same ending point. Because this conclusion and that conclusion are saying the same thing. They're contrapositive of each other. If B, then not M. If M, then not B. And the way you choose to write it doesn't matter for the purpose of solving this logic puzzle. Could we have started at, say, I? Because I see a statement that says if we start at I, we can go somewhere. We could go to D. Line 3 says I implies D. Line 2 is going to say D implies not M. And what does not M imply?
It doesn't imply anything. We essentially cut it off short, so there's nowhere for B to fall because there's nowhere for B to fall because it came before those statements, or you'd have to reverse it and put M at the beginning. Kind of like you kind of cut B out of where it had the opportunity to go at the beginning, so it can't follow afterwards.
Yeah. So we have a problem that if we had chose to start at I, we kind of get stuck halfway through. There is none of these statements, the original statements and their contrapositive, none of them say not M has to imply anything. And so you can choose your starting point to be a couple different things usually, but oftentimes some of them won't work out. Some of them will kind of fizzle out halfway through and won't get you to where you want to go. Because there's not really a way to get to B or not B or anything, the last of the four statements, if we were to start at I.
No. Is a good kind of rule of thumb for that if your original statements, like, you can start with whichever ones aren't duplicated. So like babies isn't duplicated in the statements, and managing a crocodile isn't duplicated, but illogical and despise both appear in two different statements, so that you kind of know they're in the middle.
That's a good way to do it. That's nice prediction of my next question. How can we tell in general what makes for a good starting point and what doesn't? In general, you can tell if you were to look at sort of the original set of symbolic statements, you always want your starting point and your ending point to be statements that only appear once. Ones that appear twice, like I and D. Technically here it is D, here is not D, but we can just count that as D appearing twice. If a statement appears twice like this, then we would say it has to be a midpoint of the argument rather than the starting point or the end point. So we're always with these puzzles, we want to start and end at a statement that only appears once in the original hypothesis. So Lewis Carroll, i.e. Charles Dodgson, loved to create these sorts of puzzles. He thought it was a great way to sort of test math students' minds and kind of help them to be able to construct logical arguments. Because that's ultimately going to be something that we are going to be doing, is once we get into geometry, we are going to have lots of different pieces that we could maybe string together in a variety of ways. And what we're going to be doing when we construct logical proofs is we're going to be given lots of statements that are theorems or propositions or such. We want to be able to start with one of them and be able to construct a sort of line of implications like this that ultimately will end up at a conclusion that we would like to be able to prove. And oftentimes we won't be able to get there directly. We'll have to go through and kind of get there step by step by going through some intermediate steps like this. And so Lewis Carroll really liked giving students these sorts of puzzles and as a way of doing that. All babies are illogical. Anyone who can manage a crocodile is not despised. Illogical people are despised. Therefore, all babies cannot manage crocodiles. Or anyone who can manage crocodiles is not a baby. If this is a quiz question, I would be equally happy with both those answers. Also, in constructing these puzzles, Lewis Carroll / Charles Dodgson love to come up with statements that are nonsensical, like anyone who can manage a crocodile is not despised. I don't know. I guess I can't think of any crocodile wranglers I hate, but you like to come up with statements like this that kind of are silly or don't really tell, or kind of individually are kind of meaningless. But just because the individual statements are silly doesn't mean that you can't still construct a logical argument where if these three statements are all true, then our conclusion, whichever way we want to write it, our conclusion has to be true as well. Any questions or comments about this puzzle? On Wednesday, we're going to do some more examples of these puzzles, and that will be Standard 8. Just like Standard 7, Standard 8 is really all about one thing, how to take a puzzle like this, deconstruct it, and put it together to make a single logical conclusion like this. So we'll finish off Standard 8 with a few more examples on Wednesday, and then we'll be ready for Standard 9, where we're going to start moving away from mathematical logic and looking at mathematical proof techniques. If you all have a good rest of your day, I will see you all on Wednesday.
Thank you.
Thank you.